back with our RTN network alignment session. And now we're going to talk a little bit about the actual alignment and ensuring that you have your proper coordinates. William Ohene is going to talk about the alignment process that he's working on. He's a PhD student in Civil Engineering and Geomatics at Oregon State University. He holds a bachelor's and a master's degree in geomatics and has over 5 years experience leading survey operations across infrastructure and construction projects. Now, his research is focused on automating the alignment and monitoring of real-time GNSS networks to the National Spatial Reference System. And so he's going to give a little bit about his research and what people should be doing and what managers need to pay attention for their real-time networks. So now I'll turn it over to William to present his presentation.
Thank you, Dave. I'm going to share my screen now. Like Chase and Dave mentioned, the goal of this presentation will focus on the management side of the real-time network, where we are focusing on monitoring the alignment to the NSRS and even how to align to the NSRS in the first place. And so like Chase mentioned, the RTN management software, they check the internal consistency of the real-time network. However, what they don't do is align the real-time network to the NSRS and monitor the alignment to the NSRS. So the first thing we are going to talk about is how to align to the NSRS. And the major ways NGS recommends aligning to the NSRS are: one, to either average a 10-day OPUS static solution, or to perform a network adjustment where you incorporate 10 days of 24-hour GPS data from your RTN stations. Other methods employed by RTN operators include one that I show here by the Oregon DOT, where they implement the second recommendation by NGS, where they do a network adjustment, but instead of 10 days, they use 5 days. So the key question is, does the method we use affect our alignment accuracy? And does the number of days matter? And so to answer these questions, we evaluate 3 methods. We evaluate using aligning to the NSRS using OPUS Static, using OPUS Projects, and using CSRS-PPP. For each of these methods, I combined multiple durations. And so we check combining 3 days, 5 days, 7 days, 15 days, and 21 days. And the goal is to identify when adding more days no longer significantly improves our alignment accuracy. And so for this research, we evaluate 2 real-time networks, the Oregon real-time network, and then the South Carolina real-time network. The Oregon real-time network is made up of a total of around 132 stations, 29 of them being NGS cores. For this research, we use 60 of the RTN cores within the network, and when we use 27 NGS cores. South Carolina real-time network is made up of roughly 55 stations, 10 of them being NGS cores. We use 33 RTN cores and 23 NGS cores because, as you can see in the plots, we decided to include the NGS cores in North Carolina to see how well it improved alignment. As you'd see, the South Carolina real-time network had fewer NGS cores, and that's the reason why we included some of the ones in North Carolina. And just to be clear, aligning our real-time network is basically as constraining the real-time networks to our NGS cores, because the NGS cores define the NSRS. So for each method, I'm just going to quickly walk through what we did for each. And so for CSRS-PPP, we just upload a bunch of RINEX files. CSRS-PPP allows you to zip your RINEX files, and you need to have like a maximum of 300 megabytes per upload. And the tool is able to read the RINEX header information from the RINEX file. So it's able to determine what antenna type and height it is from the RINEX data itself. We parse out those solutions after getting our solutions back from CSRS-PPP. And again, we combine those data into 3, 5, 7, 10, 15, and 21 days to see if that was going to affect our alignment accuracy. For OPUS Static, unfortunately, we can't upload a lot of files. The maximum files we can upload is 20 megabytes. And then you have to manually enter your antenna type and height. And so if you have a bunch of RTN cores, you have to do those manually. If you decide to group those RTN cores into compressed formats, all the ones you combine need to have the same antenna type and height. And after we do all that, again, we receive the solutions, and then we combine them into 3, 5, 7, 10, 15, and 25 days after removing our outliers. The final method, which we compared, was OPUS Projects. And so to upload into OPUS Projects, you still go through OPUS Static. And once you get your RINEX files or of your RTN cores in OPUS Projects, the first thing you do is you do a NGS course evaluation where you select appropriate course. OPUS Project has a user guide that gives guidance on how to do this. If you also look at the paper we wrote, you can infer how best to choose your course. After you select your course, the next thing you do is you select your baseline design, and then you begin to do the processing in OPUS Project. So in OPUS Project, you need to do, first of all, you need to do your session processing. And after you do your QA, QC for your session processing, you do 3 types of network adjustments. You do your preliminary network adjustment, you do a minimally constrained adjustment, and you do a horizontal constraint adjustment. So in total for our research, we evaluated, we did a total of 216 adjustments, combining the data into 3, 5, 7, 10, 15, and 21 days. In OPUS Projects, I should mention that when selecting baseline design, there's a multiple, like you're given multiple like choices. You can either do an MST, a minimal spanning tree, which NGS doesn't recommend, but then you can constrain just one hub, or you can constrain multiple hubs. And so because we wanted our evaluation to be robust, we try a bunch of network designs to see if it affected alignment accuracy in the end. In OPUS Project, again, we made sure we are checking our F test and our constraint ratio test. From the earlier video, Chase mentioned that you want to allow a little bit of wiggle room for some of the NGS cores, and that's determined by observing the constraint ratio test. So typically, as NGS recommends, and again, you can look at it in our report, if these constraint ratios are going above 3, you exclude them from your network and you readjust the network. And you also want to make sure that your F test passes at a 99% confidence level. So now this slide shows all of the data together. These residuals and standard errors represent the various networks we had for our OPUS projects. So we had different types of networks, like I mentioned. The blue shows our OPUS Static, and then the red shows our CSRS-PPP. And again, we evaluated this for the ORGN and the South Carolina Real-Time Network. And the key takeaway from our research was that OPUS projects gave us the least variability for both the ORGN and the South Carolina real-time network. So between those methods, and if you read the reports, it shows you the concepts behind what OPUS Static is doing. It shows you what CSRS-PPP is doing. And because OPUS Project is using adjust to do a more robust adjustment, it gave the more consistent answer all the time. And so we recommend using OPUS Projects if you want to align your real-time network to the NSRS. The second question of does the number of days matter was also answered using this plots where we see minimal improvement in the vertical beyond 7 days. The horizontal was negligible beyond 3 days. And so after 7 days, we don't see much improvement in the vertical. And based on these two plots, we make recommendations that if you want to align your real-time network to the NSRS, we advise using a horizontal constraint adjustment in OPUS projects and a minimum of 5 days, but ideally 7 days because of the vertical. During this whole process, unearthed a lot of limitations with the methods NGS recommends. It's a very tedious process. It takes a lot of time. Like you see for the OPUS Static, for example, you're limited to just 20 megabytes of data. And if you have a network of probably 100 stations and you want to do it for 10 days or 7 days, it's going to take a lot of time. OPUS Projects, OPUS Static, and some of the various tools have ways they want their RINEX files formatted. And so to go through this process, you need to make sure your files are formatted in those ways that can be ingested into these tools. OPUS Projects is powerful, but you need to interact with the tool itself. So after you perform each process, you need to check, you need to do QA/QC, you need to verify the results, you might need to rerun certain adjustments. Like I said, for the F-test and the constraint ratios, you need to make sure those are always passing. If it fails, you need to rerun the adjustment. So the entire process is tedious, and because of how tedious it is, most managers don't frequently align the real-time network to the NSRS. We should also mention some scaling challenges. OPUS Projects supports just 99 stations within the adjustment, including the NGS course. So if your network exceeds 99 stations, you might have to split your network into two to just run it in OPUS Projects. So generally, there are challenges with aligning RTNs to the NSRS, and most of them is time constraint and it's computationally intensive. And so that makes monitoring difficult. So managers can align to the NSRS, but then they don't have the time to check this alignment on a consistent basis. And so that's where Chase mentioned, as part of the ODOT and NGS project, we've developed a tool to help align or fast track this process. So the goal of this project was to integrate all the findings we have, and we build a semi-automated and eventually it will be a fully automated process whereby we align the workflow, we streamline the workflow of aligning RTNs to the NSRS, and we automate the heavy lifting, and then we allow the managers to look at the results and make decisions on the results they see. So currently we've built a way to flag misalignment to the NSRS, and then the power lies in the hand of the manager to update the network. I should mention that this research is ongoing, and so eventually the goal is to make this a fully automated process. Currently, it's still semi-automated. So this is a one workflow that goes from your raw data to an aligned position, and then we have a way to monitor this alignment. So our tool is made up of two components. We have NSRS Align graphic user interface, and this part controls our data compilation, our network configuration, and our processing and adjustment. And then we have the database that does the monitoring. So the first part controls aligning to the NSRS. The second part checks the monitoring to the monitoring of the alignment process. And for data compilation, you either provide the tool with RINEX files, or if the tool has certain sources that it supports, that it downloads. So for the ORGN, they store their RINEX files in specific locations, and the tool supports the ORGN, and so we're able to fetch the RINEX files for the ORGN. But if the tool doesn't support where your RINEX files are stored, you can provide a location of where your RINEX files are, and it will splice, resample, and prepare the RINEX files to be uploaded to OPUS Projects. And the reason why we choose OPUS Projects again is because based on our evaluation, we found that was what gave us the most consistent answer with least variability. Within the tool, you're able to define your network geometry, and then all you have to do is specify your OPUS Project processing parameters. Once you do that, the tool is going to fetch those RINEX files, push them into OPUS Projects. It will run all those different steps in OPUS Projects. It will do the QA/QC. If the constraint ratios and the F-test failed, it's going to rerun the project until we've aligned fully to the NSRS and we've met all the standards that NGS recommends while using OPUS Projects. And while this is ongoing, we extract those solutions into the database, and then the database compares that with our published coordinates, and that's how you tell whether your alignment is still, that's how you tell whether your RTN is still aligned to your NSRS. And so to give more information on how efficient the system is, so for example, the ORGN, we tested a network of 61 stations where we have 34 RTN cores and 27 NGS cores. And it took about 4 hours, 51 minutes to run that whole process from start to finish. The GUI has a lot of automated backend. And so the first thing built into the GUI is every day, it computes a daily solution. The end of the day, that daily solution is parsed into the database. And at the end of 7 days, which is what we recommend from our research, we combine those 7 days into an NSRS Align position. And we compare that NSRS Align position to what the manager has published. And if they deviate from what he has published, and we flag it when he has exceeded thresholds we define. And so if, for example, today, the tool processes and uses the broadcast ephemeris, the automated backend knows that after 2 weeks, when the precise ephemeris becomes available, it has to reprocess everything again. And so everything is automated on the backend. It's a very, a lot of meticulous work that has gone into this. And I'll show you some of the database, and hopefully that puts perspective on how the results look like. So going through the GUI, so this is what the GUI looks like currently. and it has a baseline generator where you define your network, and your RINEX download where you set up where your RINEX file is or how your RINEX file should be, and your OPUS project adjustment tab, which runs the whole processing. Like I said, the baseline generator sets up your network, RINEX download gets your observation files, and OPUS project adjustment runs the alignment. So this is what the RINEX tab, for example, looks like. You specify the day you want to run your RINEX files, you upload the stations in your RTN, for this, we splice, because we are doing splicing and resampling, you need to provide it some executables to do that. It's all detailed in the user guide. And then our OPUS project adjustment tab, this is the final tab. It creates the OPUS project. It uploads the RINEX files. It selects the NGS course based on what the user specifies. And then it runs as a session processing. It does a preliminary network adjustment. It does a minimally constrained adjustment, and it does a fully constrained adjustment. It has built-in safe in. And if you, for example, check this console output, you're able to see where it is in the processing step. The database ingests the solutions from our GUI into tables. So we have 3 tables, and then it computes residuals and generates time series plots to monitor the alignment. And then it gives a general overview of your RTN course or your stations or your network's health compared to the NSRS. So we still follow although we focus on OPUS projects, we still bring in our OPUS Static solutions. And the reason why we bring our OPUS Static solutions is we want to monitor our alignment on a daily basis. And so the OPUS Static, we use the OPUS Static and session solutions, which are daily solutions, to see how well our alignment performs on a daily basis. So every day we are getting a new OPUS Static solution, and we are comparing it to what has been aligned, what the NSRS Align position is. And at the end of that week, we combine them into a network solution and still compare that with what our NSRS Align position is. And so if we find a deviation, we flag that, and then the manager can make a decision based on the entire time series or information they have available. So like I mentioned, we have our solutions, and then we have our residuals, which are computed from whatever we output per day, and then comparing that to our NSRS Align position. We compute our residuals in our east, north, and up components. So this is an example of what the time series for our station monitoring does. So just to walk through the process, you've aligned your station, say ADEL, you have an NSRS Align position for ADEL. Your OPUS Static solution will give you your daily position compared to, or your daily residual compared to that aligned position. And if it exceeds, for example, 2 centimeters in the horizontal or 4 centimeters in the vertical, or whatever threshold we define, then that is flagged. Example of stations that have been flagged is CRLA, where we are flagging about 8 centimeters in the app component. And so this tells the manager that there's something going on with this station. And so then they're able to make an informed decision on what to do next. The network-wide alignment map gives you the overview, or it summarizes the entire network for you as a real-time network manager. So red is bad and green is generally good. And you're able to see which stations, for example, station SPRA has exceeded threshold in 2 days. So you're able to go and then look at that time series map and then make a decision. Like I said, currently what we do is we flag misalignment, and then the manager has to then evaluate this network as a whole versus the individual time series plots to make a decision on whether this is just localized or it's within a region or like the entire network is misaligned. I'm currently, as part of my research, doing a time series analysis where like I said, I currently using 2 centimeters and 4 centimeters, like in the threshold, or we can tweak it to the network. But then various networks will have like various variability. And so we want to be able to tell that from the time series itself. And so that's what I'm currently working on. And based on that time series analysis, we'll be able to provide more information to the RTN manager on how the entire network is faring compared to the NSRS, whether it's original misalignment versus it's the entire network misalignment. And based on that, they can then either update the coordinates within a specific region or just update maybe just one station or the entire network as a whole. Within the database, I don't show it, but in the user guide, we provide ways on how to update the network. We have tools that helps you export your solutions and maybe incorporate that into the RTN manager software. We have ways of updating the network as a whole, and we incorporate QA QCs. For example, when we compute the residuals, the published coordinates at the time that you compute your residuals is stored as well. So we keep track of whatever change is happening at what time. And so you're able to then look at the log file and see what changes happened when you made that change, whether you changed just a station or whether you changed the entire network. The backend stores all that information so that you have it for future purposes or future analysis. That's mostly the tool. Yeah, thank you.
Thanks, William. That was a very good presentation. Ensuring that your RTNs are aligned with the National Spatial Reference System, extremely important for obtaining accurate and reliable and consistent coordinates. So your talk is, and the material you're shown is extremely helpful to people that are trying to manage them. They're the RTNs. I know the managers, a lot of the managers don't fully understand the process. And so this will be something that will help them get a better understanding, or at least how you're recommended that they do it. We do have some questions.